Imagine a single, simple question that has puzzled scientists for generations. What exactly is a photon? We often hear that light is composed of these elusive particles, but what does that truly mean? Unlike electrons, which are defined entities, a photon is intriguingly different. It lacks mass and size, and it perpetually travels at the speed of light from the moment it's created until it's absorbed. This is not like a bullet slicing through the air. Instead, a photon is an excitation in a field that stretches across the universe, challenging our perceptions of light, matter, and reality itself. If this kind of exploration captivates you, a like or subscribe would be immensely appreciated. Let us look a little closer. To unravel this mystery, we must first journey back to the earliest attempts to comprehend light. The ancient Greeks were among the first to theorize about it. Some, like Empedocles and Plato, believed our eyes emitted rays, allowing us to see. This might sound strange today, but without modern tools it seemed plausible. Meanwhile, Aristotle proposed that light was a disturbance in the air, not something that travelled directly. These ideas dominated for centuries until Isaac Newton's pivotal experiments in the 1600s. Newton used a prism to separate white light into a spectrum of colours, revealing its complex nature. He proposed that light consisted of tiny particles or corpuscles that moved in straight lines, explaining phenomena like reflection and shadows. However, this particle theory struggled with diffraction, where light bends around obstacles, creating patterns that particles should not produce. This is where Christian Huygens introduced a revolutionary concept. He suggested that light was a wave, akin to ripples in water. Waves naturally spread out when passing through narrow gaps, explaining diffraction beautifully. This wave perspective also accounted for interference patterns, where overlapping light beams create alternating bands of brightness and darkness. Thomas Young's double-slit experiment in 1803 confirmed this wave theory, as it showed light producing interference patterns that particles could not. By the mid-1800s, the wave theory had become the prevailing view. But what exactly was this wave of light moving through, if not a traditional medium like air or water? To solve this puzzle, physicists proposed the luminiferous ether, a mysterious substance that supposedly filled all of space. It was meant to be invisible and massless, supporting light's vibrations without hindering celestial bodies. Yet doubts lingered. The concept seemed contradictory, as it had to be both rigid and fluid. Then, in 1864, James Clerk Maxwell introduced a groundbreaking idea. He showed that electricity and magnetism were intertwined, forming the electromagnetic field. Maxwell's equations described how light propagated as a wave within this field itself, not requiring any ether. Light, electricity, and magnetism were now unified under one framework. Later, in 1887, the Michelson-Morley experiment confirmed this by failing to detect ether's influence on light's speed. Light moved consistently in all directions, reinforcing the notion that the ether was unnecessary. Maxwell's theory held strong, portraying light as a self-sustaining wave of electromagnetic fields, travelling unfettered through the vacuum. Yet this was not the end. The photoelectric effect observed in the late 1800s hinted at light's dual nature. It was not only a wave but behaved as discrete packets, or quanta, challenging the established wave theory. As we journey further, we find that this duality is key to understanding the photon and its role in the quantum realm. This dual nature of light, both wave and particle, is encapsulated in the concept of the photon. When a photon strikes an electron in metal, it imparts its energy entirely in one go. If this energy surpasses the force binding the electron is freed. However, if the photon's frequency, and thus its energy, is too low, the electron remains trapped. This is why frequency, not brightness, dictates the release of electrons. Einstein's insights into this effect won him the Nobel Prize in 1921, a testament to the profound shift in understanding light. Yet misconceptions linger. People often imagine photons as tiny particles akin to Newton's corpuscles, but a photon is no such thing. To grasp its true nature, picture the electromagnetic field as a vast, ever-present lake. A photon is not a pebble tossed into this lake, but rather a ripple, a disturbance travelling across the surface. Unlike waves on water, however, the electromagnetic field is quantized. It vibrates in whole units, each one a photon. These quanta are the smallest possible excitations, indivisible and fundamental. Thus, a photon is not a composite object. It is the simplest unit of the electromagnetic field's energy. It's not something you can break into smaller pieces. Much like a musical note, a photon exists as a pure vibration, a quantum of energy with no internal structure. This challenges our everyday intuition that everything is made of smaller parts. In the quantum realm, the photon stands as a fundamental entity. In this way, the universe reveals itself not through familiar particles or continuous waves, but through the elegant fabric of quantum fields. As you ponder this, let the calm of this vast interconnected reality settle in your thoughts. As you consider this vast interconnected reality, imagine trillions of photons coursing around you. These aren't just particles darting through space, they are ripples in the electromagnetic field, each one a quantum of energy. This field spans the universe, from the light of the sun to the glow of your phone. But why do these photons never rest? Why do they always travel at light speed? The answer lies deep within the nature of mass, energy, and the fabric of space-time itself. Quantum field theory, our most profound tool for understanding the universe, tells us that particles are not separate from fields. Instead, fields are the true essence of reality, and particles are simply their excitations. Picture a calm pool of water. When you disturb its surface, ripples form. In quantum terms, these ripples represent particles. But the pool has a unique rule. Ripples must reach a specific minimum energy, or they won't exist at all. This is the quantized nature of energy. Photons, like electrons and quarks, are fundamental excitations. They possess no internal structure, unlike protons, which are complex assemblies of quarks and gluons. Inside a proton, a dynamic exchange of particles creates a chaotic environment. Yet, when we observe a photon, we see the simplest form of a field's ripple, an elegant dance in the fabric of the universe. Let this understanding of photons and fields settle in your thoughts, a gentle reminder of the universe's intricate beauty. Reflect for a moment on the elegance of a photon, seamless and whole, unlike the composite nature of protons. No matter how deep we probe with powerful accelerators, no hidden layers emerge within a photon. This elusive particle remains indivisible, a cornerstone of the universe's fabric. It serves as a fundamental piece in the vast puzzle of the electromagnetic field. So, what gives a photon its unique characteristics? The answer lies in the frequency of its field oscillations. A photon's energy is bound to its frequency by Einstein's equation. Imagine a photon of red light with a frequency of about 460 trillion cycles per second. It carries a set energy, around 3.04 times 10 to the negative 19 joules. Contrast this with a blue light photon vibrating faster at 660 trillion cycles, and thus with greater energy. Intriguingly, although photons have no mass, they carry momentum. This seems counterintuitive, for we associate momentum with mass and speed. Yet, Einstein's theory of special relativity reveals that energy and momentum can exist without mass. For photons, momentum is simply energy divided by the speed of light. Higher frequencies mean more energy and thus more momentum. Consider gamma rays. They wield immense energy and momentum compared to the gentle push of radio waves. This momentum is not just abstract, it can exert real, measurable forces. When photons from the sun strike an asteroid, they impart a minuscule force known as radiation pressure, enough to alter the asteroid's path over millennia. Similarly, spacecraft equipped with solar sails harness this effect. They capture solar photons to glide through space, propelled without the need for fuel. Photons also possess a fascinating property called polarization, often misunderstood. Picture a photon racing toward you. its electric field oscillates perpendicularly to its travel direction. If it moves side to side, the photon is horizontally polarized. These oscillations define how a photon interacts with the world. As you ponder these insights, allow yourself to drift gently into the intricate dance of photons, a testament to the universe's profound mysteries. This dance of oscillating fields brings us to the concept of circular polarization. As a photon moves, its electric field can spiral in a helix, creating what we call circular polarization. This is not an internal feature of the photon, rather it is a behavior of the electromagnetic field. Imagine a filter trying to catch such a photon. It either passes through entirely or is stopped, like a switch with no in-between state. This quantized behavior exemplifies quantum mechanics, where outcomes are distinct and discrete. Consider now the idea of photon spin. Unlike a spinning top, photon spin is a quantum trait with no classical counterpart. It's linked to polarization, with left and right circular polarizations corresponding to spin directions. Picture these spins as the essence of the photon's identity, not parts within it. They emerge from the electromagnetic field's dance, defining the photon without needing further intricacy. A photon's size is a curious matter. In the realm of quantum physics, photons are treated as point-like, lacking physical dimensions. Unlike a proton, which has a measurable size due to its internal components, a photon is defined by its wavelength. Picture this as the distance between crests of a wave on a lake, illustrating the pattern of field oscillation rather than a boundary. This wavelength helps determine interaction with objects of varying sizes, from vast radio waves to minuscule gamma rays. Yet, a photon's position remains elusive, governed by the uncertainty principle. Attempting to pin it down only increases the uncertainty in its momentum. In the end, photons are best understood as excitations of the field, their properties shaped by creation and measurement. Their enigmatic nature invites you to ponder the intricate interplay between light, energy, and the very fabric of space-time. As you reflect on these mysteries, allow your thoughts to drift, embracing the gentle and profound dance of photons in the universe. As you ponder the dance of photons in our universe, a curious question arises. Is a photon a wave or a particle? This age-old debate, known as wave-particle duality, once suggested photons could switch between being waves and particles. Imagine light behaving like a wave, creating ripples and interference patterns, then picture it as a particle, striking a detector in a precise spot, delivering energy in a single quantized packet. But here is the subtle truth. A photon is neither just a wave nor a particle. It is a quantum excitation of the electromagnetic field, a single entity manifesting both traits seamlessly. When you observe different behaviors, you're merely witnessing different facets of this singular universal field. Consider the ocean. Its waves and ripples, though distinct, are part of the same vast body of water. Similarly, every photon, whether from a distant star or a nearby lamp, is an excitation of one electromagnetic field spanning all space and time. This oneness makes identical photons indistinguishable, a principle that allows lasers to shine bright, with photons crowding into the same quantum state. Yet photons are not static. They spring into existence when the field is energized and vanish when absorbed. This ephemeral existence highlights their nature as field excitations rather than permanent objects. Unlike a rock that persists, a photon is a fleeting traveler, moving at light speed from birth to absorption. And why does a photon move so relentlessly at this speed? The answer lies in the very structure of space-time, a mystery intimately tied to Einstein's theory of relativity. Photons, being massless, must adhere to this universal speed limit, revealing deeper truths about the geometry of the cosmos. As we reflect on these complexities, let your mind drift, embracing the gentle rhythm of this cosmic dance. The dance of photons is not just about their speed, it is about their very nature. Photons are unique. Their properties, like energy and momentum, emerge from the field's oscillations. But there is something even more profound about them. Photons defy rest. From birth to absorption, they travel at the speed of light, precisely 300,000 kilometers per second. This relentless motion stems from their zero rest mass. Imagine mass as the measure of resistance to movement, as Newton described. Yet Einstein expanded this idea with his energy-momentum equation, revealing a deeper connection to space-time. For most particles, mass defines their rest energy. But for massless particles like photons, energy is inseparable from momentum. Without mass, they must always move. Visualize a photon. It cannot pause or slow down, for without energy and momentum it simply would not exist. Its motion is a fundamental requirement, not a choice. The structure of space-time dictates this, compelling photons to traverse at light speed. This is not just about speed, it is a reflection of the universe's fundamental laws. As we ponder these truths, let the elegance of this cosmic design guide your thoughts to a place of calm understanding. The universe's intricate design becomes even more compelling when we consider how light behaves. Picture yourself in a car speeding along and you toss a ball forward. The speeds combine. But with light, if you're in a spaceship moving at half the speed of light and switch on a flashlight, something extraordinary happens. The light does not travel faster than light speed. It remains constant regardless of your motion. This constancy is not an illusion. It is a fundamental aspect of our universe. Imagine space and time as a woven fabric. When you move swiftly, this fabric adjusts around you. Time stretches and distances shrink, ensuring light speed remains unchanged for everyone. This is not simply a curiosity of physics, it is a testament to the nature of space-time itself. Massive particles, like a car that can be seen at rest, are bound by these rules, able to stop in the frame of another observer. But for massless particles like photons, this rest frame cannot exist. No matter how fast you chase, a photon always races away at light speed. It is not about speed, but about the universe's very structure. Here, questions arise. What if you could ride a photon? The truth is, a photon does not have a viewpoint. The mathematics that govern our universe tell us this perspective is impossible. Concepts of time and distance dissolve at light speed. The universe's fabric leaves no room for such an experience. Photons exist and interact, yet remain beyond the familiar bounds of experience. In the stillness of this understanding, we find a profound truth. Light's behavior is not simply about velocity, but a reflection of the cosmos at its deepest level. And with this realization, allow yourself to drift into a peaceful contemplation of the universe's mysteries. This profound truth about light leads us to consider the nature of particles in the universe. Imagine holding an electron still, a feat scientists accomplish in labs. It sits contentedly, experiencing time, occupying its place in space. Now imagine pushing it faster. As it nears light speed, its inertia swells, demanding ever more energy for each tiny increase in speed. Yet no matter how powerful the force, an electron can never match the speed of light. This is a fundamental limit of our universe. In stark contrast, imagine a photon. Born of the electromagnetic field, it has no mass and must travel at light speed, never slower. This is not by choice, but by the inherent nature of the field itself. The electromagnetic field's properties dictate this immutable speed, just as air dictates the speed of sound. The photon, a quantum of light, adheres to this unyielding rule, moving swiftly and unobstructed. This distinction between massive and massless particles is absolute. Massless photons and theorized gluons and gravitons are bound to light speed, while particles with mass, like electrons and neutrinos, remain forever just shy of it. Neutrinos, once thought massless, revealed their secret mass through subtle oscillations, dancing close to light speed but never quite reaching it. This discovery reshaped our understanding, illustrating the profound impact of even the slightest mass. Finally, consider the symmetries of the electromagnetic field. These elegant mathematical structures ensure photons remain massless, preserving the harmony of the field and its unerring speed. The Higgs field, another pervasive force, grants mass to other particles, but the photon's journey is free from this influence, a testament to the intricate interplay of forces that govern our universe. As you ponder these mysteries, imagine the symphony of particles and waves, each moving to the cosmic rhythm, and let this contemplation bring you peace. As you imagine the dance of light, consider the photon, skipping weightlessly through the universe. Unlike quarks or electrons, which gain heft from the Higgs field, the photon is untouched by this mechanism. This untouched nature is what allows it to glide at the speed of light, unburdened by mass. The intricate balance of forces and symmetries confirmed by the Standard Model mandates this reality. When light seems to slow in substances like glass, it is not the photons dragging their feet. Instead, they weave through a complex interplay with matter, always at light speed. This eternal motion, dictated by the universe's very fabric, ensures the photon's role as the messenger of electromagnetic forces. This eternal motion, dictated by the universe's very fabric, ensures the photon's role as the messenger of electromagnetic forces. But what does a photon truly do in our universe? Imagine a world where every interaction and every sensation you experience is connected by this tiny quantum of light. We have learned that a photon is not a simple object. It is a fundamental particle with no substructure, travelling perpetually at light speed due to its zero rest mass. Yet its importance goes beyond merely being a particle of light. The photon carries the electromagnetic force, one of the universe's 4 fundamental forces, alongside gravity, the strong force, and the weak force. This means that every time electrons repel each other, or a magnet clings to your fridge, it is photons at work, mediating these electromagnetic interactions. Picture 2 electrons approaching each other. They do not just push apart, instead they exchange photons, resulting in what appears as repulsion. These virtual photons, different from the real ones that light up your world, exist only during these fleeting interactions. Beyond this, photons explain why you cannot walk through walls or why chemistry exists. The electromagnetic force mediated by photons holds atoms together, dictates the structure of molecules, and determines the properties of elements. Every sensation, every bond in a molecule, every beam of light is a symphony of electromagnetic interactions, with photons as the conductors. As you close your eyes and drift into sleep, remember that the universe hums with the dance of these invisible messengers, connecting the stars and the atoms within you. In this dance of invisible messengers, photons serve as both carriers and quanta of the electromagnetic field, knitting together the fabric of light, electricity, and magnetism. Imagine the precision of quantum electrodynamics, a theory shaped by minds like Richard Feynman and Julian Schwinger, where photons mediate forces with unmatched accuracy. The theory predicts the electron's magnetic properties so precisely that it's as if you could measure the distance from one city to another, down to the width of a hair. Picture an electron accelerating within a radio antenna, giving birth to photons that traverse space. These photons, encoded with information, reach your radio, transforming into sound. This same process powers the glow of stars and the warmth of sunlight, each photon a thread in the tapestry of the cosmos. When a photon meets your eye, it vanishes, transferring its energy into a chain of reactions, allowing you to see the world. In every leaf, the sun's photons fuel life itself, their energy stored in plants and released when consumed. These interactions remind us that photons are more than light. They are the whispers of the universe's energy, ceaselessly weaving through the vastness of space. As you relax into the night, consider how these tiny particles carry the stories of stars and life, an eternal journey of light and energy. As you relax into the night, consider how these tiny particles carry the stories of stars and life, an eternal journey of light and energy. But what lies at the heart of a photon? The answer is profound and shapes our understanding of reality itself. A photon is not composed of smaller parts. It is a quantum ripple in the electromagnetic field, a pure form of energy in motion. Fields, not solid objects, are the true fabric of our universe. Electrons, quarks, and photons, All are excitations of these fields, present everywhere, even in a vacuum. Imagine the chair you're sitting on. It feels solid, but that solidity is an illusion created by electromagnetic fields. Now picture sunlight warming your skin. Those are photons, massless yet essential, transferring energy. Without them, there would be no light, no chemistry, no life as we know it. Each scientific discovery has unveiled more of light's mystery. Newton saw particles, Huygens and Young found waves, Maxwell unified them into electromagnetic waves, Einstein introduced quantized packets. This unified understanding reveals photons as both wave and particle, energy and information. And yet, the journey isn't over. Theories like string theory suggest deeper truths, proposing that particles might be tiny vibrating strings. But these ideas remain speculative, beyond our current experimental reach. For now, let the mystery of the photon and its dance through the universe lull you into a peaceful rest. Imagine, if you will, the universe as a vast canvas of interconnected fields. Among them, the electromagnetic field unfolds its beauty through the dance of photons. These are not particles in the traditional sense, but the most fundamental excitations of this field. In our current understanding, shaped by the Standard Model and general relativity, a photon is a massless entity, a spin-one quantum. It travels ceaselessly at light speed, its frequency dictating the energy and momentum it carries. These photons are the messengers of the electromagnetic force, born when charged particles accelerate, and vanishing when they impart energy to matter. They are the carriers of light, warmth, and colour that touch our lives in countless ways. Picture the next dawn you witness, or the soft glow of a screen in the evening. What you perceive are not tiny objects, but the vibrations of the electromagnetic field itself, each photon a discrete note in this cosmic symphony. The field is as real as the earth beneath you, and its vibrations are the essence of reality. Stars fill the night sky, their light having traversed incredible distances. Each photon, originating from these distant fires, journeys through the vast emptiness of space. Upon reaching your eyes, their energy transforms, catalyzing a cascade of biological processes that become your perception of starlight. The photon's journey might end, but the energy persists, transmuted into the sensory experience of seeing. In this way, photons are not just carriers of energy, they're conveyors of cosmic history, bridging the gap between distant stars and your consciousness. As you rest tonight, let this thought linger. The universe communicates through these quantized vibrations, each photon a testament to the invisible tapestry of fields that shape our existence. Good night, and may the light of the universe continue to illuminate your dreams.